My name is Gon Buzaglo. I'm going to talk about analyzing continual learning from a perspective of sequential projections. We are going to discuss two papers by our group. The first one is how catastrophic can catastrophic forgetting be in linear regression? And the second is continual learning in linear classification on separable data. So in both of those papers, the goal is to analyze when catastrophic forgetting occurs and to what extent. It is done through mathematical analysis of linear models, both in classification and regression. The analysis reveals a novel connection between continual learning and a well-studied optimization framework called projections onto convex sets. It is shown that even for infinitely many tasks, there are adversarial constructions where the forgetting is arbitrarily bad. One takeaway from those works is that repetitions provably mitigate forgetting, and this is in line with existing empirical results. Finally, we will see a separation between the behavior of continual classification and continual regression. I will now describe the general setting we have studied. Given a sequence of tasks, we aim to learn a linear model sequentially and eventually succeed on all of them. So you might ask, why do we focus specifically on linear models? Well, first, it is not fully understood yet, linear models. And we believe that it is important to understand the simplest models before addressing more complicated ones. Also, since neural networks often exhibit linear dynamics in the neural tangent kernel regime, a better understanding of linear models could shed light on practical deep networks. The main assumption throughout both works is that there exists a linear model that is correct for all of the tasks. In regression, we say that those tasks are jointly realizable, and in classification, we say that they are jointly separable. More formally, we assume W star is non-empty, where W star is the collection of linear models that assign the correct label for all samples in all tasks. This is called the offline feasible set. It takes the following forms in regression to the left and in classification to the right. Note that this is a reasonable assumption in a highly overparameterized model, like wide neural networks in the neural tangent kernel regime, for example. We will be also interested in analyzing the distance of the current iterate from the offline solution, and we will focus on the mean norm offline solution for brevity. We will analyze separately the case of regression tasks, and later we'll discuss classification tasks. We will see that there are similarities and differences. Let us begin with our most important quantity, the forgetting. We define it as the mean of the differences between squared loss with respect to the last iterate and the squared loss with the iterate of every task. It can be shown that this captures the drift of the current iterate from previous outputs. Rather than proposing a new algorithmic approach, we wish to understand the simplest continual procedure exists. So we study gradient descent, where we minimize the loss of each task sequentially and use the solution as the initialization for the next task. The iterates are mathematically given by this formula here, where x dagger is the pseudo-inverse of x. Importantly, we don't actually apply this formula. We just focus on its mathematical properties as a mean to better understand the gradient descent fitting procedure. So when learning a task sequence, we are left with directions from the previous solution that are orthogonal to the current task. This is equivalent to projecting the iterate to an affine subspace, which we call the solution space of the task. Let's give it a geometric interpretation. In 2D, the solution space is simply a line. we project the solution of each task to the solution space of the next one, obtaining a recursive procedure. Since orthogonal projections are non-expensive operators, the learning contracts the distance to the offline solution, as can be seen in this illustration here. So if we will see more tasks, it seems like we should converge to the offline solution. What about the forgetting? Turns out it can be bounded by the mean of the squared residuals from the last iterate to the previous task's solution spaces. Consider the magenta arrows in this illustration. Then the bound is just their average squared size. We show a construction where both forgetting and distance to the offline solution are arbitrarily bad, even with infinite number of tasks. Essentially, the learner starts from the first solution space, up here, and then projects through those orange arrows onto consecutive solution spaces, which are very close to each other. Eventually, we reach the last solution space, which is orthogonal to the first one, causing the forgetting to be very large. Now we will see how repetitions can save the day. If the learner sees tasks repeatedly, the distance to the offline solution might still be only trivially bounded, but the forgetting can be universally non-trivially bounded. We are considering the cyclic setting, where tasks recur in cycles. This might be rather natural, for example, an autonomous vehicle that encounters the different times of the day each day. Concatenating many projection operators, we form a cyclic operator. Here we can ignore the initialization W0, it is just 0. Actually, this is a special case of alternating projections, a vast field studied in functional analysis, originated back in the 50s. For the case of two tasks, we can offer exact analysis. We illustrate here the simplified two-dimensional scenario. The solution spaces are W1 and W2. As we cycle through these tasks, we are getting closer and closer to the offline solution. The distance is precisely given by the following vector norm, which is further bounded by this spectral norm. Then we use a result from alternating projections, showing that this spectral norm equals to a power of the squared cosine of the Friedrichs angle, which is the smallest principal angle between these two subspaces. Even though this quantity should decay exponentially with the number of cycles, for very similar tasks, we would have an arbitrarily low convergence. But we should have an intuition that this is not a bad thing, since we always remain very close to the solution of the other task. This will be captured by a low forgetting. The upper bound on the forgetting is almost identical to that of the distance, with an important addition of the right multiplicative term, which makes this expression to be non-trivially upper bounded. This term also depends on all principal angles between the solution spaces, rather than only on the smallest one. Now, without repetitions, we get the following upper bound on the forgetting, which is maximal for intermediate angles, as can be seen by this graph as well. Now we show the effect of different angles on the forgetting, and we illustrate different curves for different numbers of cycles. After one cycle, as we've seen, the worst one is 45 degrees. But as we perform more cycles, the n in the bound increases, so the most destructive angles are the smaller ones, indicating similar directions among the two tasks. Now that we've understood the effect of task similarity, let's see what can we say regardless of the structure of the data. A universal upper bound is derived for the forgetting under the cyclic setting, independent of the data. the forgetting decays as the number of repetitions increases. It includes a dimensionality-dependent bound and a dimensionality-independent bound. A more recent paper improved our dimensionality-independent bound. Finally, we provide convergence result for random task orderings, which can be considered less restrictive than cyclic ones. To sum all up, forgetting can be arbitrarily bad, but is probably mitigated when tasks recur either randomly or cyclically. In the paper, you can learn about more results and connections to many other algorithms. Now let's move to classification. Again, we will see a link from continual learning to POCs, but it will be a different kind of POCs. As a reminder, our setting is almost the same, except we are learning binary classification tasks. The main assumption now takes the form of separable data. So, as in regression, we wish to understand the simplest continual procedure. We assume a regularized exponential loss is being completely minimized for each task. We also assume weak regularization of changes in the parameter space. This kind of regularization is widely used in practice, often with a weighted norm instead of an isotropic one, like in here. Our goal is to understand the algorithmic bias of this continual approach. To that end, we define another algorithm called sequential max margin, which is again just projections onto convex sets. In our main theorem, we prove that in the limit where lambda approaches 0, the normalized iterates of both schemes are equal. Note that the assumption is that lambda first approaches 0 and then fixed throughout the optimization process. This is a common technique in theoretical works. Therefore, we can now focus on the more interpretable approach, in which every task's feasible set defines a polyhedral cone. Recall that in the regression paper, we had linear equality constraints. And therefore, the projections were onto affine subspaces. Here we have inequalities. So we are projecting onto closed convex sets which are not necessarily, which are not necessarily a linear space. This makes the projections nonlinear as well, leading to a more intricate analysis. Now, the offline feasible set is the intersection of all feasible sets. This is the green area in this example. When we learn, we project the solution for the current task onto the feasible set of the next one. In this example, the iterates happen to converge to the offline feasible set. We are interested in characterizing under which conditions this behavior is guaranteed. So we use this interpretation to derive other results than those of regression. We already have an intuition that repetitions might be sufficient for this. And indeed, for two tasks in 2 dimensions, it is rather easy to see. Generally, we prove linear decay rate on the forgetting as the number of repetitions increases. This is for both cyclic and random orderings. To summarize, we showed how continual learning is linked to POCs. In the setting of regression, we had linear projections onto affine subspaces. In 2D, for a task with only one sample, this is just a line. In classification, on the other hand, we had to deal with non-linear projections onto polyhedral cones, which has a volume. Although each task brings the learner closer and closer to an offline solution, forgetting can be catastrophic. But we saw how tasks recurrence saves us. As we've seen, the algorithmic bias of continual regression is different from that of classification. Although I didn't get to show it to you, In the second paper, we also proved that popular Fisher-based regularization methods prevent forgetting in regression, but then we demonstrate that it is not guaranteed for classification. This is just one simple example to how it is not possible to directly transfer theoretical results from regression to classification. Most recent theoretical work in continual learning revolved around regression, which is more tractable to analyze. We consider our findings and call for further specific theoretical work on continual classification. I really hope you enjoyed the talk, and I hope you will read the paper. Thank you very much, and if anyone has any questions, I'll be very happy to answer.
Thank you, Gon, for the presentation.